In this video, we're going to look at what's called microcode. And note we're saying micro and not macro. So where assembly is assembly slash machine code. That's this lowest level of software, the things that one might put into RAM to execute your program. And uh, sort of microcode is at a lower level. Um, and is an intermediate between this software and the hardware, whereas macro is sort of like little sort of basically functions within assembly that so very similar words, one vowel change, but we're talking about this not the level of assembly or a little bit higher, but micro, so we're going down under assembly. All right, so the assembly is, again, this lower machine code really is this lowest level of instruction that you'll find in memory in RAM. And all of your high level code has to get down to that level. There are various ways to get down to that level: compiling, interpreting, there's linkers and loaders and all sorts of things. But so how you have to get to the level is the point here. Um, and then we have the hardware uh, are all the little pieces, and they have actions they can perform, and we have to sort of sequence those actions to achieve what we want at that the assembly level, the machine level is machine language is telling us to do. And so that intermediary is the microcode. So we get our high level program down to even the assembly, down to the machine language. It is in memory, in RAM, and then we have to work down through the control and get, which is one of our units of the computer, to get all the little pieces to act the way we want them to achieve that instruction. And so that is the microcode. So a simple instruction like load the accumulator A, put some number in a register, is going to be several microcode instructions. And this happens at the other level too, sort of, your high level language may end up sort of what may be one instruction, one statement, and your high level language may end up to be several assembly level instructions. Then the assembly level instruction may be several microcode instructions. Okay. So where is this microcode? So we said that the machine language or the assembly is in memory. Um, and then we have all these devices that do things. And then we have this code to interpret what we want to do and get it done. And that will be in ROM. So it's not, you may want to add at different parts of your program. You may want to add different data in your program. So where add is and what you're adding may change, but the instructions to make the computer add are the same. So we don't want them changing. So we put them in ROM, read only memory, where you're not going to write them, or we'll lift that a little bit and we'll say we're rarely going to change that. So we can put it in ROM and never change it, or we can put it in EEPROM, electrically erasable programmable read-only memory. So we have a mechanism for changing it if we somehow got it wrong, but we want to only change that rarely. And Flash is a version of EEPROM. And you want to do this to change those instructions fairly rarely. And so between the software and the hardware, the software we want to be readily changeable. We want to put it in RAM and easy, make that easy to write. And the hardware is what it is, and you're not going to change it unless you buy a new computer. So this microcode is in the firmware, we're going to change it. We can change it, but we're only going to do that in rare occasions. So we're going to call it firm, not quite hard, but not soft. Okay, so we have the machine language. So this is where above the microcode. And then we have this ROM. Now, ROM, I always have to say this weird expression that ROM is RAM, but RAM is not ROM. So what I mean by that is the acronym uh, of RAM says random access, and ROM is read only. And so ROM is RAM means that we can go to any the instructions or anything that is saved in ROM, we can address and access, in the way we access random access. But RAM is not ROM, and that RAM can be written to, so it is not read only. So that's that weird statement of mine. But so here we go. So ROM is this addressable thing. So that machine language can sort of effectively act as an address in the ROM. So we have the assembly, it gets assembled and put into the machine language. So the actions, the opcodes in the machine language are numbers, and those numbers could sort of serve as an address of where in ROM is the microcode for that instruction. Okay, so we have to get down to that level from our high level language, and there's a number of ways to do this. I usually just sort of simplify it and say it's compiled, but you can interpret and translate, and there's linkers and loaders. There's all sorts of things, but at this stage we don't care. Somehow our program got down to the assembly level, and then we want to talk below that how to do the microcode. What's the microcode consist of? Because at this low level, the assembly, the machine language, is what's going to communicate with the hardware. It has to be, I don't know, hardware aware. It needs to know what the pieces are, what the registers are, how big is the address of memory, and so on. So our high level languages are portable. They're always the same. The machine level has to sort of change with the hardware, at least to some extent. And you try to do some kind of backward compatibility so it doesn't change too much, but still it does change. If the hardware changes, it probably does some changing. Okay, so we're going to imagine a simple design to have this discussion of what microcode is. It is going to have what we call a bus architecture. So you have all these pieces, these registers, the memory, the ALU, and they need to exchange information. So you could have everything that might want to exchange information. You might have, some attachment between them, but that gets to be sort of inefficient, too many connections. And so we have like a central transportation system called the bus, where things don't attach to each other. They attach to the bus, and then any two things attached to the bus can exchange information. And this is the bus architecture. So we're going to have a simple bus architecture I'm showing here. We're going to go through these pieces sort of one by one and describe what they are. But we have input ports and a program counter, memory address register, memory data register, instruction register, control, the accumulator ALU, some other registers, temp, B, and C, and then we have some output. So we see here our main units of architecture. We see input, we see output, we see memory, we see the ALU, we see control. Now, in this very simple architecture we're talking about, we're just going to have one bus. Now, our program is in memory, so we're always going back and forth to memory to get our data, to get our instructions, to sort of do anything. That's where that's the changeable part. That's the programmable part. And when we deal with memory, it has values at addresses. So whenever you're dealing with memory, you have to sort of deal with the address, then deal with the value, with the data. And um, you always need those two steps, but the way our architecture is now with one bus, that address has to be on. If that address is on the bus, a value can't be on the bus. Only one thing can be on the bus. The bus is pretty much just wires connecting things, and so you can't have them interfering. You can't have an address interfering with a value. Um, but a more sophisticated architecture that we'll talk about later can have multiple buses. And then in dealing with memory, you still have to do the address and then the memory, but you can have um, somebody's address coming in while somebody else's data is going out at the same time. So you can get some parallelism or some pipelining going on and be more efficient, but not in this simple architecture we're talking about here. Okay. So we had on the upper left shown in our design the input ports. And again, we need to have things coming in, or it's not a very useful device if nothing can come in. When like everything is sort of timed and sequenced in computing, but the computer, the ALU, the processor control doesn't control when things come into input. And so we need a place to sort of hold things. So they come in, we need a place to hold them until the computer is ready to like look at it. And so that's what these input ports are. They're sort of registers holding data that's come somehow from input. We're going to hold it there, and then we'll bring it in. And I've labeled one of them as the keyboard, but the other one is just some other input. Next on our dive through this design is the program counter. It's going to tell us our next line of code or the current line of code and then set us up for the next line of code. So in memory, we have in the stored program concept, we have in memory, we have our instruction and data, and they're sort of mixed together. So we will start an instruction and we'll not need to know what instruction we're doing. But as we're executing that instruction, we're going to have to find the data it's talking about and move to other places in memory. And then it will come time to do the next instruction. And we need to know what the next instruction is. And that's the job of the program counter. As we're starting to execute instruction, to tell us what line of code it is we are getting ready to execute, and then also move on to the next one. And that's why it's a counter. So a counter is a device that has built in the ability to increment. So it will point to the next instruction, and then it will increment to move us to another place, to the next instruction. But our code is not always linear. We're not always moving to the next instruction. So we may want to branch. We may want ifs, loops, subroutines, functions. And so the program counter we have to be able to put a value into it as well as take a value out of it. And that's why that yellow arrow there has like two directions. Next down the line is sort of our memory and the registers associated with memory. And again, memory always is address and value, or I'll often call that value data. And so we have the MAR that is going to hold the address of the memory location we're dealing with. It may get that value from the program counter and be pointing to an instruction, but it also somewhere along the way may end up pointing to some data. So it's not always the same as the program counter. We have the memory, which is a large set of registers that are addressable. So we get to select one, we get to address one. And the address is held by the MAR, so we know where we are in memory. We pick that one, and then we send it to the MDR. So there's lots of things in memory, many, many registers in memory, and I don't want to have them all individually to connect to the bus. So I send the data out through a data register. So I only need the sort of the one connection to the bus. I may read data or write data, and so that connection to the MDR is bidirectional, whereas the MAR, you only tell what part of what address of memory you want to deal with. It doesn't tell you, you tell it. So it only goes, that arrow only goes in the one direction. Under that, we have the instruction register. We're talking about this level of microcode. There are many steps involved, and the instruction register holds the instruction and we'll hold it until we are done executing it. So we need to know what the instruction is. So it needs to be held there until that's done. We're going to, in this very simple, oversimplified diagram, we're going to imagine an instruction may have both an action, an opcode, and some kind of data, an operand. We're going to imagine them both going down there, but they sort of play somewhat different roles. So in a more realistic architecture, there may be multiple different registers to hold the instruction, the opcode versus the operand, but we're just imagining them going to the same place for now. The opcode, the instruction of the action telling us what to do, can serve a purpose like the MAR, in that it can sort of serve as an address of ROM. So somewhere in ROM is, and in ROM in this picture is control. Somewhere in control are the instructions to execute whatever opcode we're doing. And the instruction register is sort of holding the address, telling us where we are in ROM so we can perform that operation. The controller sequencer is the, I'll say ROM and then I'll say control, and I sometimes say controller sequencer, but usually just control. And it attaches, so it looks like in this little diagram like it's a dead end, but that's it's the opposite. It's sort of attached to everything and telling them what to do and when to do it. So that was just too hard in the diagram, so we left it out. But it really connects to everything, and it is it's where this like microcode is written and stored in ROM, and tells everybody what to do and gets everything done. On the other side, on the upper right, the ALU, I'll skip down to the ALU and come back up. The ALU is where like data gets changed to other data. It's where the actual programming and calculating gets done. And so that's where all of our, the action takes place. We're adding things, subtracting things, comparing things. All that is going to take place in the ALU. We are performing the arithmetic or the logic, the arithmetic or the logic on data, and the main location of data that we're acting on with the ALU is, it's just a register, but we give it a special name, sometimes called the accumulator. The operations of the ALU, certain things can happen. We can do a comparison, and then that might change a flag, or something may sort of go wrong. So there are various things, the ALU comparisons or overflow problems that can be indicated in the flag. Things that happen in the ALU that sometimes they're just data, and might get so an answer. If I want to add two things and keep an answer, I will put those things maybe back in the accumulator. But if I want to say I did compared two numbers, are they the same? I might put that in a flag. Or if I added two numbers and it got too high for the computer, that might be in a flag. In this, I have other registers. Temp is sort of, if I'm comparing two things or adding two things, temp is the other one that's most closely sort of like it's almost like accumulator number two. So it is um, like if I'm combining two pieces of data and getting one answer, then the accumulator will have like a slightly more important role that it will have the input data and also get the output. The temp is in this very simple architecture just has the input but not an output. And then I have other temporary locations for holding things B and C. Then finally in this design, I have the output ports. Again, that's one of the main components, one of the main units of a computer is output. It's, all for naught if you can't get something out of it. And again, these are sort of like holding places. So computers move fast. So if you need to sort of have this, if you want to display some data and actually sort of have a chance of seeing it, you want to sort of put it in some kind of register that holds it so that you can um, keep it there for long enough to see it, to either for to see some display or to send it on to storage or what have you. Okay. So let's look at one example of microcode. We're going to take one assembly level instruction called load accumulator A and break it down. Okay. So load is, there can be more than one load. So we said instructions are often opcodes and operands, and then what is the operand? What is the data? So when your load is, you're going to move information around. Um, and if we say load, we typically mean that the operand, the piece of data, is an address. So now we're going to have to go to that address, get that data, and put that data in the accumulator. We could have a variation called load immediate, where the operand is the thing we want in the accumulator. So that's an easier version. And we can have a load indirect, where the operand is an address, and then you go to that address, and there's another address, and then you get the data at that second address, and that's what you want in the accumulator. And at the higher level language, if you want to have things like variables and functions, you need that. So that sounds like complicated and ridiculous. Why would you do that? But if you know what it corresponds to in a high level language, you're like, oh, well, of course I need that. So the first, we break the execution, the microcode level execution of an instruction down into two parts. And the first part is called fetching the instruction. So we don't even know what the instruction is. So there's some part that's like always the same, and it's just getting out of memory the instruction we want to do. So the program counter is telling us where in our program is the next instruction. So we go to that program counter, but it does not attach to memory. So we've got to put the program counter's value into the memory address register. So now we're set up to get our instruction. So that's called the address state. We're going to assume that our motion through the program is linear. So the next thing we're going to do is increment our program counter. So we're ready for the next time. And now we're in our memory address register. We're pointing to the instruction we want, and we're going to read the instruction and put it in the instruction register, getting us ready to actually execute that particular. So something's executing here, but we're executing the fetch. And so it's not particular to what we're doing. It's just that we always have to get what we're doing in order to be able to do it. Okay, so these first three are sort of always the same. So this has nothing really to do with load. I'm only now ready to do the specifics of load because now I know that that's what I want to do. So just pictorially, the address state was moving a value from the program counter to the memory address register. The increment state was just incrementing that program counter, setting us up for the next time. And the memory state was taking that address, getting the sort of activating the register with that address in memory, sending its value out through the memory data register and into the instruction register. Now we're ready to actually do load accumulator A. So again, in this, this is going to require two steps. So we said that instruction, the data part, the operand of this type of instruction was an address. And so what do you do with addresses? You put them in the memory address register. So our next step is going to take the operand part of our instruction out of the instruction register and move it up to the memory address register. And then once the address is set, then we want memory is always address then value. So now we set up in step 4, we set up the address. Now we're ready for the value. And we said we want that to go over to accumulator A. And then other instructions might take longer. So sometimes you imagine that this simpler instruction, uh, just to keep things even, you might say that there's a sixth step, but it's not to do nothing, to do no operation, no op, and just sort of pictorially take the operand part, the data part of the instruction, which is an address, and throw it in the memory address register, and then go to that address in memory, grab the value, and put it through the data register onto the bus and over to the accumulator. And there we have it. So that gives you an idea of microcode. We described a simple, overly simplified architecture and sort of said, like, here's a very simple instruction, move some data over to the accumulator, one of the register closely associated with the ALU. And we saw that took a number of steps, and that's just the way it is. Thanks for your attention.